Changed. All right. Happy Thursday. It's Thursday, week 3. We're doing chapter 5 today. Um, Hopefully, you all have completed the test. Well, it's due tonight at 11:59, so hopefully that's done. I haven't checked, so hopefully that's done. This is the material starting for the next test. So today is going to be all about probability. We've been doing a lot with statistics. Today we're going to do probability. And I do want to mention, because it's the beginning of this recording, I want to mention that this weekend I will be going out of town. So I'm leaving tomorrow. I'll check in the morning, but I'm leaving tomorrow and I won't be back until probably midday Sunday. I will try to check it from the hotel Saturday night, maybe tomorrow night, but I can't guarantee my availability. So just letting you know this weekend I'll be mostly unavailable. Um, we're going to the Oregon Zoo and then we're going to the aquarium in Newport, so it should be super fun with my daughter and a couple of grandkids. So today we've got 5.1. We're just going to be kind of talking about the empirical method and the classical method, what those two methods are, and how to calculate those probabilities. A little bit of terminology here. This is going to feel very disconnected from what we've been doing, but it will tie in pretty well with what comes after now. So we're going to have this disjointed piece right now, and then I'll build on it and it'll make sense where it came from. So 5.2, we're going to look at the addition rule for disjoint events, and then for the general rule. Then we're going to talk about the complement rule, which is something super important. Then 5.3, we're going to look at the multiplication rule and how to identify independent events, and then what at least probabilities look like. At least is an area where people struggle a lot. Hopefully, I'm able to make sense of it for you, and I'll do my best to answer questions when I can. So that is today. Ouch, sorry, my cat just attacked me. That's today, and we'll get started. Let me get my iPad opened up. Okay. Uh-oh, cancel. All right. So starting with a little bit of terminology and different ways to talk about events and outcomes, and I'll show you which one you're going to be expected to know for the test. So first, let's talk about the outcomes. So this is a very tedious way about talking about all of the outcomes of a probability problem. So if I'm running a probability experiment, in this example, we're rolling a die, you list each one. So event 1 would be rolling a 1, event 2 would be rolling a 2, event 3 would be rolling a 3, etc., etc. Think about how tedious this would be if we were doing it for a deck of cards. You would have to do 52 different possibilities, 52 different outcomes. I will not ask you to write your outcomes like this. I will never, ever ask you to do this. It is just super tedious, but this is a way to list all the outcomes. The other way is sample space. This I will be asking you to do. I will be asking you to write down the sample space. So the sample space is a set. We use curly brackets, and then inside the set, you write down what all of the possible outcomes are. You just list them with commas in between them. Rolling one die, it's super simple. You just say 1, comma 2, comma 3, comma 4, comma 5, comma 6. If you have rolling two separate dice, there's going to be 36 different outcomes. Flipping a coin or flipping two coins, there's going to be or four different outcomes. I'll show you what that looks like in a minute. So depending on what you're doing, you need to show every option. So in this case, order matters. So if I was rolling two dice, I'm not going to do all 36 of them because that's just ridiculous. But if I was rolling two dice, I'd have 1, 1, I'd have 1, 2, I'd have 1, 2, but also 2, 1 is a different roll. That's ugly. 2, 1 is a different roll than 1, 2, because if the first die is 1 and the second one is 2, the second option is the first dice is 2 and the second one is 1. So these would be two separate options. Then I'd have 2, 2, or I'd have 1, 3, but then I'd also have 3, 1, etc., etc. So it's two separate outcomes. That's why we get 36 with rolling a dice, with rolling two dice. So that is something really important to think about. I'm saving the flipping coins in a minute. All right. So if we're defining an event, we're defining what a success looks like. So my event here is to roll an even number. So then I would need to write down what the possible outcomes are for what the successes look like. So rolling an even number, I could roll 2, 4, or 6. So, for example, with if I was rolling a pair of dice and I wanted to roll all of the options that add up to 6, so I could have an event and it could be add to 6. Then my event is going to look like this. It's going to be, I'd have 1, 5. Whoops. I'd have 1, 5, but then I'd have 5, 1. Then I would have 2, 4. I'd have 4, 2. And then I'd have 3, 3. These would be all the different ways that I could roll 6 on 2 dice. So you need to show me both directions. All right, questions before I move on? All right. Something weird's going on my other computer. Hold on a second. There we go. Okay. So empirical probability is also called experimental probability. Experimental is the word, the way I used it. Now that's spelling probability wrong. Let me see here. Experimental is the way I learned it. Our curriculum calls it empirical, but I want you to know both of them just because out in the wild, you might hear experimental rather than empirical. And experimental means you are actually throwing the dice. You're actually flipping the coins. You are actually pulling cards out of a deck of cards. You are doing the experiment. You are running the trials. So that would be, you'd be experimenting and you would do a whole lot of different repetitions in order to get what that probability would be. So what we do for experimental probability is we just create a relative frequency. So remember, a relative frequency is how many times something shows up over the number of like total items there are. So here it's how many times we got a success over how many times did you perform the experiment. So let's say that I rolled a dice 35 times, and it's just a number I pulled out of my head. I rolled the dice 35 times. That's my total number of trials. And let's say that I got an even number 16 of those. So 16 out of 35 would be the probability, in this case, based on my empirical evidence, based on my experiment. 16 out of 35 is my probability of rolling an even number. Now we know that really it's 50%, but this is based on our experiment. Now, if I did this experiment over and over and over and over again, I did it 1,000 times, it's going to get really close to that 50%, which is the actual probability. So if we're actually performing the trials, that is our experimental probability. We're actually doing the trials. Okay. I thought I was going to do the heads and tails thing. I'm going to just do it here. So if I rolled two dice, if I flipped 2 coins, I'm flipping 2 coins. I'm just going to write this here. And these are fair coins. And I want to know what my sample space is. So my sample space, we generally use a capital S. It doesn't really matter. My sample space is going to be, I could get heads and heads. I could get heads and tails. I could get tails and heads, or I could get tails and tails. There's 4 separate outcomes because this right here, these are 2 separate things. I could either get heads and tails or I could get tails and tails. So technically there's a 50% chance of getting 1 heads and 1 tails. That's why we have to write it out that way. because if I'm computing that probability, I need to make sure that I'm accounting for both of those. Okay. All right, let's move on. So I don't know if you've ever played the game Pass the Pigs. It is a really fun game. I actually bought it for my AP Stats class at the high school because I learned about it in this class and then had to do a deep dive on the internet because it's what I do and thought it was fun, and it actually is pretty fun. So instead of dice, you roll pigs. You have these cute little pigs. One side of the pigs has a dot on it, and the other side doesn't. And there's different ways that it could land. And the probability of them landing different ways is different on each one. Because obviously, the pig just landing on its side is going to have a different probability than it landing up on its snout with its feet in the air. It is. And so we rolled, or a class of 52 students rolled the pigs 3,939 times. And they kept track of how they landed. So we're going to actually calculate the probability of each outcome here. So you just calculate this the same way you calculate relative frequency. So I would do 1344 divided by 3939. I don't know how I got this weird stuff on my screen and weird stuff in my calculator. Hold on a second here. Oh, my grandson was playing with my calculator. That's how the weird stuff came on my calculator. Okay, so this is about 34% or 0.34 and 1294. So we just do this with each one of them. This is the same thing with when we did relative probability or relative frequency. It is the same math. We're just calling it something different, and I did something wrong here. Queen of typos strikes again. I'm just rounding to 2 decimal places. I'm going to talk about the properties of a probability model in here in just a minute. And I believe it's going to be on a different screen as well, but now is a perfect time to talk about it, about what are the pieces of a probability model, because you will on your next test, you're going to have to identify whether something is a probability model or not. I know it's weird. I'm talking about the next test when today's the due date of this test, but it is what it is. All right. So I built this probability model here, and there are a few different things that every probability model are going to have. So this is what you're going to look for. Every probability is going to be between 0 and 1. So each probability, I can't spell apparently. Each prob, I'm not going to write it out, between 0 and 1. And I think that there's a list later on, but I'm writing them down. So each of these numbers is between 0 and 1. I can't have a probability of 113%. I can't have a probability of -4. I can't. So they all have to be between 0 and 1. The next thing, all of your probabilities are going to add up to 1. Now I rounded here, so they would be slightly off. If I added these numbers together, it's going to be slightly off because I rounded. But they're going to all add to 1, which is 100%, because it makes sense because this is 100% of my outcomes. I'm going to add these together and see what they end up being. I know it's going to be off because I have one of them to 3 decimal places and then the rest to 2. Yeah, I have 98.8, and that's okay because I rounded. It's okay that it's slightly off. If I added them up and it added it up to 0.73, there's going to be a problem. But if it's really close, then rounding is a factor. So I rounded, so I have 98.8. That's okay. And there's a third thing, and I can't remember what it is. So between 0 and 1, and they add to 1. there's a third thing. We'll get it on the other screen because for some reason in my brain, and this might be just the two, for some reason my brain is not getting me there. All right. So our probability model shows you the probability of each of these outcomes based on our experiment. Now we did 3,939 rolls. So this is probably really close to the actual probability because we have such a large number. So the law of large numbers tells us that as the number of trials gets bigger, the closer we're going to get to the actual probability. Just like I said, if we kept rolling dice over and over and over again, if I rolled dice 3,939 times, about 50% of those are going to be even because we're getting close to the actual probability. All right, I'm going to move on where I already have this. So let's talk about this. We want to look at the probability that a thrown pig lands on the side with a dot. So we're looking at our probability model right here is the side with a dot. So that probability is 0.33 or about 33%. Now, my open math is going to ask you for both. Occasionally, it's going to want the decimal. Sometimes it's going to want the percent. Just pay attention to what it's asking for. I don't care which one you give me. If you give me the percent, that's fine. If you give me the decimal, that's fine. So on my test, I don't care what you give me, but my open math cares. So pay attention to how they want you to put that in there. So now let's look at leaning jowler. It wants to know if it would be unusual. So this is something important. If a probability is less than 5%, it is considered unusual. Any probability less than 5% is considered unusual. So think about our empirical rule that 95% of our data is between two standard deviations of the mean. Anything outside of that, anything in the other 5% is an outlier. That's kind of where this comes from. So anything with less than a 5% probability is considered an outlier. So a leaning jowler would be unusual because it occurs less than 5% of the time. Same thing with snouter. Snouter is at 3%. So it is also unusual, but trotter is not because trotter is 9%. So anything that occurs less than 5% of the time is considered unusual. I'm going to write this down because words in writing help. Anything that occurs less than 5% of the time, that's a really ugly 5, is considered unusual. There we go. Very important. I'll give you a second if you're writing that down, and then I will move on. All right. So let's build another probability model. I'm going to have you get started on this, and then I will slowly, quietly work behind you. So you're going to build this probability model. So this is represents 200 people who are asked how they travel to work. So your number of trials is 200. We want to know how many of them do each of these things, or what percent, or what the probability is. So go ahead and build your probability model. I'll let you get started ahead of me, and then I'll work quietly behind you. I didn't do any rounding here, so this would add up to 100% or add up to 1 because I didn't do any rounding. I didn't need to because all of them are 3 digits. That's what the beauty of having the 200 in the bottom. So all it means when interpreting the result. So it says estimate the probability that a randomly selected individual carpools to work. So what this means, I'm taking a look at this and it's 0.11. So 0.11 is my probability or 11%. So what this means is if I randomly selected a commuter, I randomly selected a person, there's 11% chance that that person carpools. It's 11% chance. That's what the interpretation is. So if I randomly selected a person, 11% chance that they would carpool. Or another way that you could interpret this is if I randomly selected 100 people, I would expect 11 of them in that 100 to be carpoolers. Now, this is obviously estimation because we have a sample of 200 people. That's not super large, but this is based on our experiment. This is experimental probability based on our experiment. So number C, would it be unusual, sorry, to randomly select an individual who walks to work? Take a look at that. Would that be unusual? Yes, you're right. Because walking only occurs 2.5% of the time. Right, thank you, less than 5%. Because walking only occurs 2.5%, and that's less than 5%, it would be unusual for somebody to select an individual who walks to work. That would be unusual. Good job. All right. Are we good? Can I move on? Okay, good. All right. So, the classical method of computing, it's also called theoretical probability. That's the way I learned it. They call it the classical method. I call it theoretical probability. I kind of like it better, but maybe it's just because I learned it calling it theoretical rather than classical. So we have to have equally likely outcomes. So our rolling pigs or how people travel to work, those aren't equally likely outcomes. So you have to have equally likely outcomes, and then we can use that for our probability. Okay, so this is the way that we calculate with theoretical probability or the classical method. I'm going to write theoretical up here again. Theoretical probability. Man, my writing is getting worse and worse. Okay, so we know that everything has an equally likely chance to happen. So we first need to know the number of possible outcomes. So if I had a bag of M&Ms and there were 45 M&Ms in there, there are 45 different outcomes, 45 different things that I can get. So it'd be out of 45 M&Ms. So the number of possible outcomes. And then the number of ways our event can occur is on the top. So if I have a bag of 45 M&Ms and 8 of them are red, then 8 would be the number of ways that I could pull a red M&M out of there. So that's how we calculate our theoretical probability. Or rolling dice. If I'm rolling 2 dice, there are 36 different possible outcomes. So we have 36 on the bottom. And the number of ways we can roll 6. I don't remember what that number was. So whatever that number was, the number of ways we can roll 6 would be on the top. So that is our number of ways it can occur over the number of possible outcomes. Let's do some examples. This is going to be helpful. I need to take a drink. Getting a headache. Okay. So, as I said, bag of M&Ms. So we have a fun-sized bag of M&Ms. In that bag of M&Ms, we have 9 brown candies, 6 yellow candies, 7 red candies, 4 orange, 2 blue, and 2 green. So if we randomly selected, we want to know the probability that it is yellow. So I need to add these numbers up. So 15, 22, 26, 28, 30. There are 30 candies in this fun size bag of M&Ms. So my denominator is going to be 30 because there are 30 different outcomes or 30 outcomes, 30 different candies I could grab when I grab one out of there. Probability it's yellow. So we have 6 yellow candies. So I have 6 yellow candies out of 30. If I simplify this would be 1/5, which is 0.2 or 20%. Sometimes they're going to ask you to leave it as a simplified fraction. That's absolutely fine. Sometimes the fractions are easier to work with. Now we want to know the probability it's blue. Once again, we keep the 30 because there's still 30 M&Ms and there's 2 blue ones, which gives me 1/15, which is 0.067 approximately. Now it just wants me to, it says to comment on the likelihood of getting the candy being yellow versus blue. All it wants here is to say you're 3 times more likely to get a yellow candy than a blue candy because there's 3 times as many yellows than blue. Makes sense? Are we good? I've got more. I think I have another example. All right. Yes, I do. See? Okay. We rolled 2 dice. We want to know the probability of rolling a 7. So I'm going to circle these. I'm going to circle the 7s. There we go. Kind of circles. So out of 36, there's 36 different ways to roll the dice. Because remember, 3, 2, and 2, 3 are 2 different ways. So therefore, I have 36 as my denominator. I have 1, 2, 3, 4, 5, 6 different ways of rolling a 7. About 0.17 approximately. So we have about a 17% chance of rolling a 7. Now we want to know snake eyes. I've had students in the past not know what snake eyes are, which is weird to me, but I'm also an old fogey, so I know things that people don't talk about anymore. So snake eyes is just rolling a 2. It's just rolling double ones, so it's rolling a 2. So it's 1 out of 36. Let me find what that fraction or decimal is. So 0.03. Definitely unusual, right? Because it has less than a 5% probability. So we have a 17% chance of rolling a 7, not unusual, and a 3% chance of rolling snake eyes. That is unusual. So we want to comment on the likelihood of rolling a 7 versus rolling a 2. You are 6 times more likely to roll a 7 than a 2. Makes sense? We doing good so far? You just have yes already typed in, right? And you just hit enter every time. Because I'm going to ask. Not quite. You're like, that's a good idea. I just need to do that. All right, let's move on. Okay, we're in 5.2. That was 5.1. That was it on 5.1. That was fairly quick and painless. So let's move on to 5.2. All right. So we're going to learn the OR rule. That's what I call it. It is the addition rule. We're going to learn the addition rule, or we call it the OR rule. You'll see why in a minute. If 2 events are disjoint, they don't have any outcomes in common. You've probably heard mutually exclusive. Mutually exclusive means the 2 things can't happen at the same time. If I flip one fair coin, I can't flip both a tails and a head at the same time. If I roll one dice, I can't roll both an odd and an even number at the same time. They're mutually exclusive. They both can't happen. So that's what disjoint or mutually exclusive means in this case. So we're going to start with disjoint, and then we're going to move on to not disjoint and what that looks like with this rule that we're going to learn. Okay, here's the addition rule when things are disjoint. So this is the OR rule. The reason I call it that is because you're going to see the word OR with this rule. The addition rule will always have the word or. Okay, so for or probabilities, this is what we do. We take, if I said, for example, what is the probability of rolling a 3 or rolling an even number? I would take the probability of rolling a 3, then I would add it to the probability of rolling an even number. You add those two probabilities together. If they are disjoint, you add them together and then you call it good. I'll show you what that looks like. I have an example. Now, if I had a whole bunch of disjoint things, if I was like pulling things out of a deck of cards and I said, what is the probability of pulling out a 2, a 3, or a 4? I can add all three of those probabilities together. As long as they have no outcomes in common, you can just keep adding them together. If you had 30 different things and they're all disjoint, you just add them all together. It is the same thing. You don't change the formula as long as they are disjoint, as long as they're pairwise disjoint or none of them have anything in common. Okay. Oh, I thought it was it was not. All right. So we have a probability model right here for number of housing units, number of rooms in a housing unit. And so they just counted up how many there were in this housing unit. Every single, if I was to list, like, let's say all of the addresses to all of these housing units or the number apartment numbers, and I put them on pieces of paper and I threw them all in a hat. Each one, pulling each one out of the hat has the same probability of being pulled out of the hat. Every single apartment has the same probability of being pulled out. So see, there were only two things. I don't know why I thought there were three. Okay, so all the probabilities have to be between 0 and 1. They are. And trust me, all of these add up to 100%. This is a probability model. So that's the first thing that we want to do. We want to know the probability of randomly choosing a two-room apartment or a three-room apartment. So I'm going to do the probability of 2 plus the probability of 3. So I want to know what's the probability of randomly choosing a two-room unit or a three-room unit. So I just take those two probabilities and I just add them together. I don't trust my adding right now. I don't know why, because it's so easy to make little errors when you try to do things in your head, especially if you're talking at the same time. So these add up to 0.125. So the probability of randomly selecting either a two-room unit or a three-room unit would be 0.125 or about 12.5%. So this is really easy when they're mutually exclusive. When they're not mutually exclusive, when they have something in common, it gets a little bit more complicated, but not a lot. It's not a lot more complicated. It has one more little piece, and I'll show you why that piece is there, and hopefully that'll help in your brain. The why part will help you. So I'm a big why asker. I always want to know, well, why does it work? Maybe that's why I majored in math. Oh, wait. I want you to try this one on your own and like 2 coins. Right. So, oh, for the not mutually exclusive, is that what you're talking about? Um, it could be. We're gonna do you'll see. You'll see. We'll do that in a minute. So this one is these are mutually exclusive. So we want to know the probability of just drawing a king. And then the probability, you do not need to simplify your fractions. And then the probability of drawing a king or a queen or a jack. So go ahead and start working ahead of me. And then remember that there's 52 cards in a deck. If you want to simplify, that's fine. Okay. So right, 113, good. So the probability of just a king is 113. So go ahead and now do probability of king or queen, or queen or jack. This one's actually fairly simple because they're the same. So it's 3 13s because there's three of them. So it was king, queen, or jack. Yes. Makes sense. Are we okay? Yeah. No worries. No worries. Okay. Now we're going to do if they're not mutually exclusive. So when they are not disjoint, we still keep the probability of the first one plus the probability of the second one. We still keep that, but we have to subtract off the overlap. I'm going to show you why. It's going to make a lot of sense once I show you why. So you do the probability of E plus the probability of F, and then you subtract off the part of them that are not disjoint. So the part that they have in common, that's what we're subtracting off. And I'm going to show you why. I'm going to use colors because it's fun. And I'll show you why. But go ahead and write down the formula, and then I will show you the why behind it. Now my next screen, I believe, might be different than yours. So now the picture's the same, but I changed the problem and I didn't change it on yours. Okay. No, maybe not this one, but the next one, the dice I think are different. This one might be the same. So we want to know the probability of drawing a king or drawing a diamond. Obviously, we have a king of diamonds. So let's take a look. So I'm going to highlight the kings. I'm going to highlight them. We're going to highlight them yellow. I'm highlighting the kings. So the probability of a king, I'm going to write this down. So probability king or diamond. So I highlighted the kings. That's 4 out of 52. Okay, that's my first highlighting. I'm going to highlight the diamonds. Highlight the diamonds, highlight the diamonds. There we go. Now the diamonds, there's 13 diamonds. But this one right here, this king of diamonds right here, that king of diamonds, he was counted twice. He's highlighted twice. So I counted him in the 452 and I counted him in 1352. So I counted him in both of them. So I need to subtract one of them off because I counted it twice. That's why we do the subtraction, is because I counted it twice. So 4 plus 13 is 17 minus 1. So I have 16 out of 52 or 4 out of 13. So we're not really like getting rid of something, we're just getting rid of the double. All right. Let's go. Now let's try with our dice. And so I believe this one is the one that has a different problem. So with our dice, we're looking at the probability of rolling a multiple of 6 or the probability of rolling a double. So we have probability, I'm going to do like this, mult of 6, or, remember that or word, doubles. So I'm going to circle because it's easy, a little easier than highlight. So let's do multiples of 6. I love that everything is on diagonals here. So here's 6. These are the 6's. There's the 6's. And then we have 12. So we have the 6's and we have 12. Okay. Now I'm going, so that right there, I have 1, 2, 3, 4, 5. There's 6 out of 36. So now let's look at rolling doubles. Rolling doubles again are on a diagonal. So let's just count those. 1, 2, 3, 4, 5, 6. 6 out of 36 again. I'm using my highlighter. This one is double counted, and this one is double counted. So I have 2 of them that I counted twice. And I counted them in the purple and I counted them in the pink. So I have to subtract off the 2 out of 36. So it makes the most sense not to simplify your fractions until after you've done your addition and subtraction, because currently we all have the same denominators and you're not always going to have the same denominators. So you can just add them across because it gets confusing and difficult if you simplify first. So 6 plus 6 is 12 minus 2. That gives me 10 out of 36, which is 5/18. So that probability would be 5/18 if you want to get fancy, and it could be 0.28 if you want to get fancy. So you have about a 28% chance of rolling either a multiple of 6 or doubles. Questions on this one? All right. I will move on. Okay. So the complement rule is something that we're going to be carrying with us. And the complement rule is, it's super simple. You already do this. You just don't have a name for it. You just don't say, hey, I'm going to use the complement rule. It's just something you automatically do in your head, but it's something that does become important. And just the complement is not like the probability of something not happening. So if I had that the probability of something happening was 30%, the probability of that thing not happening would be 70%. That would be the complement. So it is just the probability of it not happening, the not outcome. So if the complement of E would be not E. So for example, here, the probability that a randomly selected household owns a dog is 31.6%. So the probability that somebody doesn't own a dog would be 1 minus 0.316, and that's going to give me the probability someone doesn't own a dog. 0.684 or 68.4% chance. So it is just the probability of not, basically. So that's the complement rule. So if there's a 25% chance that somebody's late to work, there's a 75% chance that that person's going to be on time to work. So that's what the complement rule is. It's the probability of it not happening. Okay. Sometimes we use the complement rule because it's just easier. It's the easier math. So sometimes we do that. Like for example, here, we have all of the probabilities of like it's the commute time for a whole bunch of residents in Hartford County. So this shows the frequency of each of those. So the probability that somebody has, I'm going to go backwards on this one. We know that the probability of somebody having a commute time of 90 or more minutes is this right here. I calculated that, just took the 4895 and divided it by the total number of people that I have. And so the probability of randomly selecting a person that has a commute of 90 or more minutes is 0.015. Now, if I wanted to know what is the probability of randomly selecting a person who has a commute of less than 90 minutes, I could either calculate all of these probabilities and add them together, which would be a whole lot of work, or you could do 1 minus 0.015. So I'm going to write this down. Probability less than 90. I'm not going to write minutes out because why? So that would be 0.985. It just makes sense to subtract it from the 100% or from 1 rather than figuring out all the other ones and adding them together. That would be a lot of work. Using that complement rule just makes sense there. And we're going to put the complement rule in your pocket for right now. I'm going to bring it back out at the very end of the lesson. This is a good place to start it, but it's going to become really important at the end of the lesson. So go ahead and put it in your pocket, and I'm going to bring it back out later. This is the end of 5.2. Whip. I guess it isn't. I'm going to have one more example. 25% of a deck of cards have a suit of hearts. What is the probability you will not draw hearts? Right. So we do 1 minus 0.25. Yes, you can do 100 minus 25, which is what you did in your head. And it's 0.75 or 75%. I know you just did 100 minus, which is perfectly fine. Go ahead and do that. This one is a super easy one to do in your head. They're not all that easy. All right. So are we okay right now with the complement rule? So I can move on to 5.3? Okay, perfect, perfect, perfect. All right. So we've finished 5.1 and 5.2. We are in our last section. This is moving really quickly. We are probably going to be done maybe even before 6:30. That's crazy. Just moving right along. Sometimes this one moves really fast and sometimes it doesn't. Okay, so we're going to put the or rule, put it away for right now. Go ahead and put that one in your pocket. We are going to learn the and rule, but first we're going to talk about independent versus dependent. The and rule is where a lot of people have some confusion. So I'm going to try to move through this one a little bit slower, especially when we get to the at least probabilities. We'll move through that a little bit slower. So if two events are independent, the probability of one occurring does not affect the other one occurring. Like if I flip a coin and then roll a dice, as long as they don't hit each other while I'm doing it, the probability of one happening doesn't affect the other one. If two events are dependent, then the probability of one affects the probability of the other. So, two people driving in a car together, the probability, I know this is morbid, but the probability of one of them getting in the accident obviously affects the probability of the other one getting in an accident. Those would not be independent. Those would be dependent. It does work. Yes, if I'm understanding your question correctly, the dependent ones, yeah, they don't affect each other. So like if I had a person driving their car in New York and a person driving their car in San Francisco, one of them getting in an accident doesn't affect whether or not the other one's going to get in an accident. Does that make sense? The dependent ones, if two people have the same commute every day and they leave their house at the same time, one of them getting in an accident is not independent of the other one getting an accident because they could be encountering each other. They're going to be encountering the same road conditions, even though they may not even like be right behind each other. The probability of one getting in the accident could affect the probability of the other one getting in an accident. They're not far enough removed from each other, if that makes sense. I have another example of that in a second. So let's look at some examples. Okay. So you draw a card from a standard 52 card deck, and then you roll a die. The events draw a heart and roll an even number. These are independent. The result of choosing a card doesn't impact the dice tossed, and vice versa. One is not going to affect the other. Those are independent. Now, this one right here, okay, this one makes sense. Two 40-year-old women in the United States are randomly selected. The events woman one survives the year and woman two survives the year are independent. So these are independent because the 40-year-old women, there are a lot of them in the US. I don't know how many, but it is a huge number. I'm not likely to randomly select two of them that are in each other's lives. They randomly selected two of them in the whole United States. It's not likely that they are in each other's lives. So those would be independent. However, letter C, two 40-year-old women live in the same apartment complex. The events woman one survives the year and woman two survives the year are dependent. So they may never encounter each other. They might not, but their paths could cross. One of them could spill a glass of water outside of her apartment and cause the other one to slip and fall down the stairs. Their lives intersect, so we can't call it independent because they could affect each other. There is that possibility. So we can't call those independent because they're too close, if that makes sense. I'm not going to nitpick, like give you these weird examples like this, like that are that really make you think like that. You're more likely to get examples like this. You're more likely to say to get things that are more obvious. I'm not going to try to be tricky like I am here. Because I do not make a habit of like tricking people with my questions. That's not me. I would much rather really test your knowledge rather than trick you. Now, if I was going to give you a bonus question, now that would be tricky. That's I do trick people if I give bonus questions, which sometimes I do, sometimes I don't. Usually in summer I don't, but you never know. So summer is just so jam-packed anyway. It's like I don't want to add that extra little burden. But anyway, let's move on. Okay, here's we're determining whether these are independent or not. Suppose you flip a coin twice. On the first flip, it lands on heads. The second flip, it lands on tails. Are they independent or are they dependent? They are independent unless you like got jelly on your hand for the first flip or something. Yeah, they're independent. So are the events earned a bachelor's degree and earned more than $100,000 per year dependent or independent? Dependent, right? Because you're more likely to earn more than $100,000 per year if you have a bachelor's degree, unless you're a teacher. But yeah, you're more likely. It definitely helps. Okay. Two 24-year-old males in the United States are chosen at random. Male one gets into a car accident during the year, and male two gets into a car accident during the year. Are these independent or are they dependent? Right? They're independent because there's a lot of 24-year-old males in the US. They probably randomly chosen in the whole US. You're not likely to get two of them like that are in each other's lives. These would be more questions I would ask you. So this would be more along the lines of what I would ask you. None of these are tricky. Questions on this before we move on to the math? All right, let's move
I
on.
have a question. Can you hear me? Hello?
I can hear you. Yes. Can you hear
So
me?
what we're looking at, are we looking at the variables? Okay, we're not looking at Z score. This is like, I know I'm trying to go back because the brackets are like, the
This
classes.
is disconnected from anything we've done yet. This is
Okay,
a new topic. Disconnected. I'm going to be building on this on the next section. So this is
okay,
separate from what we've already done.
okay.
Yeah. We're in 5.3 right now. It's um independent is more like the unusual one. Eh, I mean, I don't,
It just feels very similar, like slight variation of what
yeah,
we're
it's
studying with a calculator, but
completely different.
we're not doing two step, we're doing three or four step like variables.
No, we're not doing any of that. We're doing probability. So the less likely something happens, yes, yes. It's kind of like 5.1 where we're saying if something happens less than 5% of the time, it's unusual. There's a less than 5% chance that I would choose two 24-year-old males that would interact with each other. Yes. Yes, your comment in the comments. Yes, perfect. All right. So multiplication rule for independent events. So we are not going to have a rule for if events are not independent. It is a very complicated process that we are not going to do. We're only doing independent events. So first thing you need to figure out is, are these events independent? If events are independent, we multiply their probabilities. And I frequently call this and probabilities because the word and is going to be in between the two probabilities. So these are and probabilities when you see the probability of this happening and this happening. So two things both have to be true. And so we multiply their probabilities. We multiply the probability of E times the probability of F. So this is the multiplication rule, and this is for and probabilities when you see the word and. Okay, so let's do some examples. So the probability that a randomly selected female aged 60 years old will survive the year is 99.186%. So we want to know the probability that two randomly selected females, 60-year-old females, will survive the year. So we need the probability the first survives and the probability the second survives. So we're using the same probability because each woman has their own probability. The probability of this one surviving is 99.186, and the probability of this one surviving is 0.99186. So we're going to multiply those together. So the probability of both of them surviving is 0.9838 or 98.38% once we multiply those together. We're going to do more examples. Okay. Suppose you flip a fair coin twice. We want to know the probability you flip a head on both flips. So we would need the probability heads and heads. So we'd take the probability of heads, and I know this is a lot of writing for just multiplying 50% times 50%, but I need you to have the process. So the probability of flipping heads would be 50%. The probability of flipping heads is 50%. When we multiply that out, we get 25%. So whoops, that's a 4. That's really ugly. Let me rewrite that. Okay. The probability of flipping heads twice, so getting heads the first time and getting the heads the second time, is about 25%. So you just multiply those together. They each have their own separate probability because they are independent. We are going to do more of this, but are there questions so far? Okay. So this is math that manufacturers actually do, especially when they have defects in their equipment. So in this case, this manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers are going to actually use the equipment in the first year after it's purchased. So if there's a 1-year warranty on the equipment, they want to know what proportion of customers are actually going to make a valid warranty claim. So we need to know the probability it is defective and used. So what's the probability it is defective and it is used by the consumer? We need to know the probability both of those things are true. So the probability it's defective is 0.10, so 10%. The probability that it was used by the customer is 30%. And you just math it out. And I know I can do this math in my head, but sometimes. So there's about a 3% chance that the product is defective and that the consumer used it within the first year. So based on what we learned earlier, if something happens less than 5% of the time, it is considered unusual. So this manufacturer most likely is not going to spend money to fix whatever the defect is because it's going to only be about 3% of the time that it's going to be that they're going to make a warranty claim. So the thing is, if you even there could be even another probability. What is the probability that a person has a defective product and they make a claim? Because most people like will say, this is way too it's way too cumbersome to make a claim. So I bet you that would even reduce this more. So why would this manufacturing company, why would this company even fix their problem, spend all the money to fix their problem if they're not likely to get claims? So this is math that's used for stuff like that. No questions before we move on?
So it's like all our processed returns and refunds. That's how they use the map to make sure it's profitable for them to help us.
Yep, that's
So
exactly.
insurance claims are also like on the list when your house burns down or you're flooding or some natural disaster, they'll use the same estimate.
Yeah, that's so there's actually a job called actuary. So an actuary, they actually start off in the high five figures. So they're like probably close to $100,000 a year starting wage. And they sit in rooms all day and calculate probabilities of accidents happening in different situations. And it's their job. They're calculating these probabilities all day long. That's what they do. And and that helps them to determine what makes sense for insurance claims. That's
How
like,
do they, how does, so then how do insurance companies make money? Is it just because they overcharge everybody or give different rates?
well, you'll see. We're gonna do one with life insurance here in a minute, and you'll kind of see what it's going to look like. That's a great question. If you can hold it just for a few minutes, you'll
No
see.
worries.
You'll see exactly why. No, that's perfect. Perfect segue into to getting to the previous new examples, other examples we have. That was perfect. Thank you. All right. And actually, this is it right here. No, there's another one coming up. So, probability that a randomly selected female will survive the year is 99.186%. We already know that. We want to know what the probability that four will survive the year. So, I would like you to calculate this, four of them. So, I want the probability one survives and two survives and three. I'm going to just do RV and you do the same thing. Uh-oh. If I could write it correctly. Actually, the life insurance is next week. Sorry. I forgot there's something else I need to teach you before we do that. So we take all of these and you just multiply 0.99186, all of these. That's ex Oh, you rounded. Okay, that's good. It's fine. I didn't say what to round to, so you're good. So couldn't I have just taken this and did this? And you may have done this already. Can't I just do this to the fourth power? Isn't that the same thing? Isn't that the same math? It's math that makes it a little bit easier. That's what you did? Okay. So there's a little button and you right above the division sign. Looks like an upside down chevron. It is called the caret. And you use the caret to get to get an exponent, which is going to be super helpful right here. Compute the probability. Okay, so we're going to do an at least probability. This is something you're definitely going to want to write down. This is something super important. This is something that people really, really struggle with. So I might even do a separate whole new example afterwards. So every time you see the words at least, you're going to use the complement rule. I'm going to say it again. Every time you see the words at least, you're going to use the complement rule. In fact, I'm going to write it down. Every time you see the words, you will use the complement rule. Every single time you see those words. And it doesn't matter this chapter, next chapter, the chapter after, 2 weeks from now, a month from now, next class you're in, every time you see the words at least, you're going to use the complement rule every time. And the thing is if you send me a message through Blackboard, which obviously Blackboard or my open math, obviously I want you to send it to me if you're struggling. I'm going to type this sentence right here. If you send me a question and say, I can't figure out this at least probability, I'm going to type this sentence and then I'm going to help you. So every time you see the words at least, you'll use the complement rule. So remember the complement rule is for the probability of something not happening. So we know that the probability of a randomly selected 24-year-old male surviving is this, that he survives the year. That's the probability. We want to know that what's the probability that out of 1,000 males, at least one will die. What's the probability at least one will die? So I'm going to start by writing that. The probability at least one dies. So the probability at least one dies. So we need the probability not all 1,000 live. I need the probability that not all 1,000 of them live. So what that would be, it's going to be 1 minus the probability all 1,000 live. Wait, not all 1,000 live. Wait, I just did that backwards, didn't I? No, I didn't. 1 minus the probability all 1,000 live. So, okay. So I take the probability that all 1,000 of them are going to live, and then I do 1 minus that. So if the probability that one of them dies, that they die is 0.9986, the probability they live
Yes.
is 0.0014, correct? So the probability they live, oops, I just did that backwards. The probability they live is 0.99. I just did that backwards. I was thinking of backwards. Don't worry about it. Okay, so we're going to do 1 minus 0.9986 to the 1,000th power. Take probability all 1,000 live and then do 1 minus. So you can just type it in like that. 1 minus 1,000. Nope. 1 minus parenthesis 0.9986 caret 1,000. Put that in your calculator. Okay, so I got 0.7536. So out of 1,000 people, there's a 75% chance at least one of them will die. That's kind of morbid, I know, but
Well, hospitals are full of people.
that's true. That's true. I mean,
There's still a lot of people running around making more humans,
it's
but it's just more like the thing with humans after they age at a certain age bracket. It just gets more and more
well, I mean, and the
possible.
thing is that at 24, they're still driving recklessly and all of that stuff. So it's quite, you mean, it definitely could
I
happen.
don't even have a car, so I don't drive recklessly.
Okay. So any questions on what I just did here? Because we're going to do another one.
So does it mean it's infinitely smaller or infinitely larger when it comes to analyzing all this data? So you have a greater chance, or it means that it's super small, or it's just 1% that you die.
I mean, yeah, I mean the probability of one person dying was 0.0014. But when I have 1,000 of them, there's a 75% chance at least one of them dies. Now I'm not choosing which one. I can't say which one, but out of 1,000 of them, there's a 75% chance at least one of them were going to die. All right, let's do the next one. Okay. Now, this one is kind of confusingly worded, so I'm going to try to walk you through this a little bit. So, among 21 to 25-year-olds, 29% say they have driven while under the influence of alcohol. Suppose that we have three that are selected at random. What's the probability at least one of them has not driven under the influence of alcohol? Okay, so every time you see the words at least, you'll use the complement rule. The words at least are in here, and so we're going to use the complement rule. I always start by writing out what I'm looking for. We want to know the probability at least one has not. I don't need to write all of the words out, but at least one has not. That's lovely. So at least one has not. That means it's the probability not all three have. So the probability at least one didn't drive under the influence of alcohol is the same thing as the probability that not all three have driven under the influence of alcohol. Therefore, we do 1 minus the probability all three have. So it's 1 minus the probability that all three of them have driven under the influence of alcohol. Once we do, I think this is the last slide, but I'm going to go to a homework problem and we're going to work through a homework problem together before we wrap it up. Okay. So what this looks like, 1 minus 0.29 to the third power.
And it's because we have three different values that we go do it to the third value.
No, it's because there's three different people. We have three people in our sample.
Oh, okay.
Yeah.
Ah, okay. I see that little
Yes.
word.
Yeah, because we have three people in our sample, we're raising it to the third power.
Oh, makes sense.
0.9756. So the probability that at least one of them has not driven under the influence of alcohol is about 97.6%, which is great. Even though I really hate this statistic that 29% have driven under the influence of alcohol. I don't like that number. That's too big of a number. But it's realistic thinking about 21-year-olds and how they think they're still invincible. So it's kind of realistic, unfortunately. Right, before I go to a homework problem, any questions here? Because I think that we need to do at least one more of the at least.
Okay, so that 0.9756 is the survival rate, or what is the final
It's,
0.9756?
this means this is the probability that at least one of those three people has not driven under the influence of alcohol.
Oh, okay.
So that's the answer.
Can you write that down? Probably of
Yeah,
people
I
not
can write a
drinking because
sentence.
it just it's like putting an answer right there without
Yeah,
specifying it gets really confusing if I try to. Thank you.
97.56% chance or probability. I hate chance because chance is actually a different calculation. At least one has not under the influence. I'm not going to write alcohol. I'm out of room. Okay. See, take the chance that all DUIs subtract from one. Yes. Yes, yes, yes. Exactly. Good. Good, good, good. All right. I'm going to go to one of our homework questions because I think that's going to help because it's directly from our homework. So I'm going to go and it's the one I get the most questions about. So I'm going to pop over to that. No, I thought I already had that open. So you're going to have to bear with me a second while I get into my open math. Okay. So I believe it's in 5.3. It's a vaccination question. Okay, let's see if I find it. No. Yep, this one right here. Okay. I'm going to just write some notes on my iPad so I can pop back over there. So in a large population, 54% of the people have been vaccinated. If 5 people are randomly selected, what is the probability at least one of them has been vaccinated? So I'm going to write these things down and then I'm going to go back to my iPad. This is directly from your homework. So 54% have been vaccinated. Okay, out of 5. You're going to have different numbers, which it makes this even better. We want to know probability at least one has been vaccinated. Okay. I'm hoping that it's already in your brain every time you see the complement or every time you see the words at least, you use the complement rule every time. Okay. I'm going to pop back over here. So 54% of people have been vaccinated. We're taking a sample of 5 of them. We want to know the probability at least one has been vaccinated. So now what we're looking at is the probability not all 5 are vaccinated. If you've ever taken a class that has done any like logic, you kind of see that we're like flipping it around. So the probability not all 5 are vaccinated. So what we need then is 1 minus the probability all 5 unvaccinated. So here's the tricky part. They gave us the vaccinated rate. So we need to think about what is the unvaccinated rate. So if my vaccinated rate is 54%, what's the unvaccinated rate? I'm going to pick a different color. And in my corner over here, yes, 46% are unvaccinated. This is the tricky part of that question. 46% are unvaccinated. Therefore, we would do 1 minus 0.46, and you don't have to put it in parentheses. It's just what I do to the 5th power. That's going to give you that probability. Look at you doing all this math right there. 5th power. And you are right. 0.9794. So there's a 97.94% chance at least one of those 5 people is vaccinated. I will write this, I'll write the final thing because that might be helpful. Out of 5 people, the probability that was ugly, that at least one is vaccinated is 97.94%. Yeah, that's why I chose that question to go over because that's the one I get the most questions about. That's the one that I have the most messages. So I figure grab it and go through it here because you're going to get different numbers anyway. So it's kind of tells you to pay attention to the wording that sometimes they get kind of tricky. One other thing I want to point out, questions on this problem before I jump back to the homework assignment.
So you see the little information pieces and then you see the number of like how many, and then you basically you turn it into an exponent problem, and then you subtract it from a one, and then you get your answer, and then you move that decimal 2 points to the right.
Just pay
Uh,
attention to how my open math wants it though, because here they want it either 3 decimal places or a fraction. So they don't want a percent here. Sometimes they'll ask you for a percent, sometimes they won't. So pay attention to how they ask for it. But so here I put it in a percent because for me, I don't care. but my open math cares, so pay attention to that. I want to go up to crunchicles. This right here, um, this right here, these are going to be a little bit different. You're going to be creating fractions, and the these are non-independent things, and so you need to just grab the numbers from the table.
Wait a second, so you have to do one per category. Every category has its own similar one
Well,
that we have to break down per
so
for the
our total population is 500 down here, but
yeah.
we have 268 people that are 55 and over. You have 69 of them that are 30, 5 to 55. And then over here, there's 168 of them that like Crunchicles. So you need to pay attention to what it's asking. So like for just a second here. So
You still
this,
have to put like one minus whatever number you get on the categories, and then you have to kind of send it to whatever it is, how many people there is, like to the exponent.
well, these ones are not at least. These are just the regular ones. These are not at least. But like pay attention to um so like right here, given that he or she dislikes Crunchicles, this changes your population. So it says what is the probability a consumer is 8 to 24 given that he or she dislikes Crunchicles? Your population is now out of 87 people, or out of 168 people that like Crunchicles. This given right here shrinks your population. So you're going to take, I would take 40 and divide it by 168 because given that he or she dislikes Crunchicles, that changes your population to the 168. So pay attention to when it says given. I think that's the only one that says given. Yeah. Oh, no, this one right here. If a selected consumer is 70 years old, what's the probability he or she likes Crunchicles? That one also changes your population to the 55 and over. So we have the 268, and it was a dislike that he likes. So you would take the likes Crunchicles and put it over the 268. So pay attention when it's looking at a specific population. So if you get stuck when you're on that problem, send me a message. I'm happy to help you. I just
Like
wanted
you
to
need
point.
more explanation because the categories are a bit where I'm not sure how to do one minus the
As
population
I said,
sample of
this
total
one
and
doesn't
then
have
do
that. As I
oh,
said,
okay.
question one is not at least. There's no at least on this, so don't worry about the complement rule because there's no at least. It just wants you to use the numbers from the table.
I need to see a problem worked out from one section and then it'd probably help me in everything else. It just is kind of like fuzzy right now.
And so you're just going to just grab the like I mean I just kind of just did that for you with this one right here.
Okay.
Given that they like Crunchicles, so it changes your population to 168, so that's your denominator. The probability they're 18 to 24, so your numerator would be the 40. So it'd just be the 40 over 168. That's what you would put in here. Or but
Oh,
I
so it'd be like 11 over 82 or 36 over
yeah,
250 or
yeah, you're
87
gonna
over.
yep, you just simplify that fraction.
Oh, okay.
I don't know if
So
you guys know this, but if you're not good at simplifying fractions, your calculator can do it for you. Take a look here. So I'm going to do 40. Uh-oh. Okay. 40 divided by 168. Take a look here. I want to simplify this fraction. So I'm going to do math, hit the math button, and see this first one here that says fraction. Hit enter and then enter, and it gives me a simplified fraction. It is just the coolest thing. So any fraction that you have, if I had 360 divided by 1848, I could do math, choose the fraction option, enter, enter, and it simplifies the fraction for you. It's really cool. All right. That's all of the material that I have here for tonight. Any questions that you want on the while it's recording? Any questions while recording
I
about?
had a question about the last, like the problem we just finished kind of going over it.
Uh-huh.
So should the strategy that you showed us about putting fractions, should I do it for every single age group until we stop at the total?
Well, you don't need to do that. You just do what just the questions that are asked. You don't need to do every single one. I'm just
Okay, because
yeah, I just showed you how you can simplify a fraction on the calculator. So
I was overthinking of doing every single category
no,
kind of
that's gonna be
fraction.
way too much work. You're only gonna do 4 calculations here, so that's way too much.
Okay, I'm just
Unless you want
overzealous.
to for
Like
fun, but otherwise don't do it.
I'm over thoughtful because it's what we call mass saturation.
Yeah,
Like it's like if you have all these probabilities and you're not sure in order which is the correct one, you do all of them, and then you find out all this like in case you miss, you probably have something correct.
yeah.
But I don't know if it's basically
Don't do
based
that.
on assumption versus facts,
Yeah,
but
don't
you
do that.
shouldn't do that.
All right.
Okay.
Any other questions while we're recording? Okay, I'm gonna turn off the recording if I can find that button.
I
Oh,
have ones for after class, after the recording is done,
I'm
though.
gonna
That's
turn the recording off right now.